NumPy performance, uint8 versus float and multiplication versus division. I have just noticed that the execution time of a script of mine nearly halves by only changing a multiplication to a division. To investigate this, I have written a small example. This prints the following timings. I always thought a multiplication is computationally cheaper than a division. However, for uint8 a division seems to be nearly twice as effective. Does this somehow relate to the fact that 0.5 has to calculate the multiplication in a float and then casting the result back to an integer? At least for floats, multiplications seem to be faster than divisions. Is this generally true? Why is a multiplication in uint8 more expansive than in float32? I thought an 8-bit unsigned integer should be much faster to calculate than 32-bit floats. Can someone demystify this? Edit. To have more data, I've included vectorized functions, like suggested, and added index iterators as well. The vectorized functions are much faster, thus not really comparable. However, if timeit_iterations is set much higher for the vectorized functions, it turns out that multiplication is faster for both uint8 and float32. I guess this confuses even more. Maybe multiplication is in fact always faster than division, but the main performance leaks in the for loops is not the arithmetical operation, but the loop itself. Although this does not explain why the loops behave differently for different operations. Edit 2. Like at Jodeci already stated, we are looking for a full explanation of division versus multiplication and into uint8 versus float, or float32. Additionally, explaining the different trends of the vectorized approaches and the iterators would be interesting, as in the vectorized case, the division seems to be slower, whereas it is faster in the iterator case.
The problem is your assumption that you measure the time needed for division or multiplication, which is not true. You are measuring the overhead needed for a division or multiplication. One has really to look at the exact code to explain every effect, which can vary from version to version. This answer can only give an idea what one has to consider. The problem is that a simple int is not simple at all in Python. It is a real object which must be registered in the garbage collector. It grows in size with its value, for all that you have to pay. For example, for an 8-bit integer 24 bytes memory are needed. Similar goes for Python floats. On the other hand, a NumPy array consists of simple C-style integers/floats without overhead. You save a lot of memory, but pay for it during the access to an element of NumPy array. AI means a Python integer must be constructed, registered in the garbage collector, and only then it can be used. There is a lot of overhead. Consider this code. A mult.ly1 is 25 faster than a mult.1 because integers in the list are already Python ints and don't have to be created. The lion's share of the calculation time is needed for creation of the objects. Everything else can be almost neglected. Let's take a look at your code. First, the multiplication. In the case of the uint8, the following must happen. I neglect +5 for simplicity. A Python int must be created. It must be casted to a float, Python float creation, in order to be able to do float multiplication, and casted back to a Python int or / in uint8. For float 32, there is less work to do. Multiplication does not cost much. 1. A Python float created 2. Casted back float 32. So the float version should be faster, and it is. Now let's take a look at the division. The pitfall here, all operations are integer operations. So compared to multiplication, there is no need to cast a Python float, thus we have less overhead as in the case of multiplication. Division is faster for uint8 than multiplication in your case. However, division and multiplication are equally fast / slow for float 32, because almost nothing has changed in this case. We still need to create a Python float. Now the vectorized versions. They work with C-style raw float 32s / uint8s without conversion, and its cost, to the corresponding Python objects under the hood. To get meaningful results, you should increase the number of iteration. Right now the running time is too small to say something with certainty. Division and multiplication for float 32 could have the same running time, because I would expect NumPy to replace the division by 2 through multiplication by 0.5, but to be sure one has to look into the code. Multiplication for uint8 should be slower, because every uint8 integer must be casted to a float prior to multiplication with 0.5 and then casted back to uint8 afterwards. For the uint8 case, the NumPy cannot replace the division by 2 through multiplication with 0.5 because it is an integer division. Integer division is slower than float multiplication for a lot of architectures. This is the slowest vectorized operation. P.S. I would not dwell too much about costs multiplication versus division. There are too many other things that can have a bigger hit on the performance. For example, creating unnecessary temporary objects, or if the NumPy array is large and does not fit into the cache, then the memory access will be the bottleneck. You will see no difference between multiplication and division at all.
This answer only looks at vectorized operations, as the reason for the other operations being slow has been answered by E. A lot of the optimizations are based on old hardware. The assumptions that meant that optimizations held true on older hardware do not hold true on newer hardware. Pipelines and division. Division is slow. Division operations consist of several units that each have to perform one calculation one after another. This is what makes division slow. However, in a floating point processing unit, FPU, common on most modern CPUs, there are dedicated units arranged in a pipeline for the division instruction. Once a unit is done, that unit isn't needed for the rest of the operation. If you have several division operations, you can get these units with nothing to do started on the next division operation. So though each operation is slow, the FPU can actually achieve a high throughput of division operations. Pipelining isn't the same as vectorization, but the results are mostly the same, higher throughput when you have lots of the same operations to do. Think of pipelining like traffic. Compare 3 lanes of traffic moving at 30 miles per hour versus 1 lane of traffic moving at 90 miles per hour. The slower traffic is definitely slower individually, but the 3-lane road still has the same throughput.
It's because you multiply an int by a float, and store the result as an int. Try your r_mult and r_diff tests with different integer or float values for the multiplication, division. Especially, compare multiplying by 2 and multiplying by 2.
It's a very first operation that will typically take longer before warming up, for example memory allocated, caching. See the same effect using the reverse order of dividing and multiplying.
If you want to see more, please consider subscribing.